So first of all, my sincere apologies for how this first version of this video went. I'm re-recording this and I appreciate your patience as we work through some of the kinks in the process. This is again base excision repair, and a lot of this is going to look familiar in some ways, the process to nucleotide excision repair, the major difference being that we're not removing the entire nucleotide. All we're doing is removing just the base, hence base excision repair. This is going to be, again, a repair mechanism that is for damage that can't be repaired by a single enzyme like the photolysases. This is specifically going to be the primary repair pathway for deamination, oxidation, and alkylation damage. Base excision repair is nice because just like nucleotide excision repair, it's going to be just about the same in all organisms. And the enzymes, of course, are going to be the major difference. These enzymes will also play a role in single-stranded break repair. The base excision repair pathway removes just the base, and it's going to remove and replace just the base, meaning that it's going to cleave the N-glycosylic bond and remove the base while leaving the sugar phosphate backbone intact. So again, similar in some ways to nucleotide excision repair, but not quite. Base excision repair is going to use DNA glycosylases. There's two major types of DNA glycosylases, and both are going to work via a similar mechanism to the photolysases, in that they're going to flip the damaged base out of the helix and cleave the N-glycosylic bond, which is right here. So monofunctional bases will just cleave the N-glycosylic bond, and bifunctional glycosylases are going to cleave the N-glycosylic bond and also cleave the bond between the sugar and the 3' phosphate. The repair is going to follow a slightly different pathway based on which enzyme is going to cleave the N-glycosylic bond. So here we've got our monofunctional enzyme. It's going to come in and it's going to just remove the base by cleaving the N-glycosylic bond, which would have been here normally. And on this one, we're going to see the bifunctional enzyme that's going to remove the base and also cleave the 3' sugar phosphate bond. So glycosylases aren't super specific. They're just going to recognize that there's a damaged base, and so they have what we call broad specificity. So we're going to look at base excision repair following a monofunctional enzyme, and it, just like nucleotide excision repair, starts with the recognition of a damaged base. And the first thing that we're going to mention is that we're looking at eukaryotic repair enzymes in the names of the enzymes. So once the base is recognized, it's going to be flipped out by DNA glycosylase and recognized and cleaved. So here we've got the hydroxyl group remaining. This creates an A-basic site, A-P site. We call them apurinic and apyrimidinic sites. This means that it's a site that doesn't have a base, and this becomes important later on as we talk about the mismatch repair, because there are ways to deal with this if it's not completely fixed. So the the glycosylase is first going to come in, cleave off the base, and then an AP endonuclease is going to cleave on the 5' side of the of the A-basic site. So this is different than the bifunctional enzyme, which would do the glycosylase and the endonuclease activity at once. So this leaves a 5' deoxyribose end and a free 3' OH end. So there are two different ways by which we can repair this. The first is a short patch repair, and that's going to be DNA polymerase beta. So again, we had this free 3' end, and the polymerase is available to and able to catalyze the addition of one base directly to that end. The polymerase beta is also going to remove this 5' phosphate end. This leaves us with a single strand nick, and DNA's ligase will ligate the nick. So the DNA that base excision repair starting with the bifunctional enzyme will be very similar to this pathway and can be actually seen in figure 12-13. So again, we have DNA polymerase beta is going to put this base in, then it's going to cleave off the phosphate end, and DNA ligase is going to seal the nick. The other option is a long patch repair where there are several nucleotides that are repaired. This is going to replace 2 to 8 nucleotides. So it starts with the same 3' OH and 5' phosphate as with short patch. But instead of polymerase beta, we're going to get polymerase delta or epsilon, which is going to add a whole bunch of base pairs. And this is going to add the base pairs using this sliding clamp PCNA. The PCNA is going to help also to cause the separation of the old patch off of the strand. And so we wind up putting in 2 to 8 nucleotides. So we get, this is called a flap. So a flap endonuclease is going to come in and cleave off at this phosphodiester bond here. We're left with a 3' OH and 5' phosphate, and of course the DNA ligase is going to come in and repair it. So again, this is going to be very similar to what we see for this part is different from the bifunctional enzyme. So reminder to look up the bifunctional enzyme in figure 12-13.